recently, as Sinha sir said, they are receding at a very rapid rate. So when we talk about glaciers, we also talk about ice caps. Ice caps are essentially smaller glaciers, if you may. These are dome-shaped masses. So you can think of a glacier being made up of multiple ice caps. They typically cover less than 50,000 square kilometers or so. And then you have ice sheets, which are thin layers of ice, thinner layers of ice compared to glaciers or ice cap, but they extend over very large tracts of ice over very extensive areas. For example, Greenland, Siberia. These are all examples of ice sheets. So, regardless of whether we call it ice sheets, ice caps, or glaciers, we're talking about an area that is largely covered with snow for most parts of the year, if not the entire year. In many cases, it is all the time, but there are a few places where that is not the case. If we look at geographic extent, they tend to be near poles, but they don't have to be near poles. Dr. Sinha talked about the third pole being the edge gauge range, edge gauge system. So they cover about 10% of the area. And if we add to this some snow-covered mountains and snow-clad mountains, you will pretty much see them in every continent except perhaps Australia, but you will see most of this in many places. Okay, so as I said, snowpacks, these are found on mountainous areas. They're not as big as glaciers, but they undergo the same process, except in the glaciers, we had water from the last ice age that became glaciers. These are more snow that is accumulating in more recent times on an annual basis, if not. So again, these are very important sources of water, particularly in the Western United States, where I work. Snowpack melting is what gives a lot of that water. About 33% of the northern hemisphere is covered with snow seasonally. Of course, if you go to southern hemisphere, things do change quite rapidly. It's only about 2% or so, nonetheless important. So we all know about glaciers melting, glaciers receding, and if we look at the cumulative loss, it correlates very strongly. You will see a very significant drop happening since 90s, and perhaps very accelerated since 2010 or so, and that corresponds very much to the rise in mean surface temperature or the global temperature that we have seen since 1990s, which is where I'm pointing to, and you're seeing a much steeper growth since 2010s, which is what governs right here. So glaciers have lost about 267 gigatons of ice per year. So that's quite a bit of surface water that's being lost by glaciers. If we look at sea level rise, which is a problem that's associated very closely with glacial melting, about 50% of sea level rise, or 53% to be more exact, is due to glacier melting, and the other 40% or so comes from thermal expansion of oceans. Greenland accounts for about 21% of sea level rise, melting of ice sheets. Antarctic ice sheets are about 13%, and other glaciers contribute about 21%, including the glaciers in India that Professor Sinha talked about. So when we talk about snow-capped mountains, typically we try to lump them into a broader area called the cryosphere, or frozen earth or frozen space, if you may. So melting of cryosphere actually has a very positive feedback loop with global warming. It actually increases global warming. This is because ice are basically white substances, so they are white. So there is quite a bit of albedo, or reflection of shortwave radiation. And when we start melting glaciers, we are exposing the earth underneath, which tends to be darker, or they are melting into water, which also tends to be darker. So there is quite a bit of absorption of heat, and then that heat that's absorbed in the shortwave radiation of the solar radiation is reflected back as a long waves, long wave radiation, which gets trapped by the presence of greenhouse gases in the atmosphere. So glacier melting not only is caused due to global, climate change or global warming, but glacier melting does cause global warming as well. So it's important to monitor glaciers from that perspective. If we look at precipitation, which is the driver of hydrologic cycle, cryosphere melting, of course, increases the amount of water. If all things being the same, if you increase the amount of water, you increase evaporation. And we just saw that melting also reduces albedo, which in turn increases the global temperature, which again increases evaporation or evapotranspiration. But one of the problems with this increase is the increase is not uniform. Unfortunately, we are seeing greater rainfalls in areas that already have substantial amount of rainfall. So it's not that glacier melting is necessarily helping us on a global scale. Arid and semi-arid regions still continue to suffer from droughts, greater variability of rainfalls, and lack of wetness, whereas places that were already wet are experiencing greater rainfall events, which causes different problems such as flooding and others. Not only does it change the amount of rainfall, but it also changes the timing in precipitation. This is really big, particularly from an agricultural standpoint. In North America, we get a lot of the winter precipitation through polar jet stream. When the polar jet stream gets altered, places that do get snow, and when we get snow, changes quite a bit. So we're seeing delays in when we start seeing snow accumulating on our mountains, which in turn can be a problem because we want that water to melt later on and provide us with water when we need it. So if that timing is low, a lot of times we get smaller melts. California, for example, experienced a very prolonged drought a few years ago, and that's because of the lack of sufficient snow accumulation in the Sierras from where they get their water. Back home, even in India, changes in monsoons are being noted, which again plays a very important role in sustaining agricultural activities, as well as urban water supply, as well as uh, maintaining stormwater discharges in urban areas. The other aspect where cryosphere melting has importance is as these glaciers melt, they cause freshening of ocean water, which means they reduce their salinity and reduce their density. And this in turn affects some of the deeper circulation or the movement of the water within the ocean or the mixing within the ocean, which helps with which is density driven, temperature driven, hence thermohaline circulation, and that in turn causes changes to amount that is evaporated and the type of rainfall that we get. Particularly West Africa or Europe are seeing significant differences in when they get rainfall due to changes in thermohaline circulation. One very important watershed in the U.S. Is the Rio Grande River watershed. Rio Grande is the fifth largest river in the U.S., and it starts in Colorado and flows all the way across the U.S.-Mexico border. It gets into Mexico and comes all the way down to Texas before it merges with Gulf of Mexico. A lot of this water here is because of snowmelt that takes place in Colorado and New Mexico. So what has been happening in recent years is that snowmelt is